So yeah, so we can start share screen. There. Can you see min skärm?
Looking perfect.
Great. Okay, also another thing is that you understand that we, as I said yesterday, there is a lot of things here going on. You can just look about the number of the slide that we have. We had 143 slides, and this is kind of common for all the classes. Det er masse ting som vi må studere i dette fag, men så for meg det fint. Jeg kan prøve å snakke norsk, men I go a little slow. Så det kan skje at vi har ikke tid å gjøre alle ting på PPT hvis jeg snakker norsk. Så i dette tilfellet dere må studere disse ting alene. Så dere kan bestemme det. Så vi kan starte nå med forelesning på norsk, da vi skal se. Kanskje etter break, vi skal se hvis vi har masse slide eller PPT at vi må gjøre, da jeg kan kanskje skifte til engelsk, så vi kan gå litt mer fast. Men dette er også is also another reason why I prepared the video, because hvis dere vil at jeg snakker norsk, da jeg har ikke tid å gå gjennom alle ting. So in the video instead, there are all the things that you have to study. So, and this is the video that I uploaded, which is the one that you have to kind of like, all the information are there. Så dere kan bestemme det. Jeg kan starte på norsk. Hvis dere er OK at jeg snakker engelsk, vi skal gå faster. Men jeg kan snakke på norsk. Dere kan bestemme det. OK, så i dag vi skal studere Cmos digital kretser. Og så jeg skal lære dere hvordan man kan analysere og designe en Cmos digital krets. Så vi skal studere hvordan man kan bruke transistorer på digital kretser. I digital teknikk dere brukte FPGA, men i dette fag vi skal bruke ikke FPGA. Vi skal bare bruke elektriske komponenter og lage digital kretser. Så disse elektriske kretser med elektriske komponenter kalles typisk hardware. Men software har dere skrevet med VHDL på FPGA kalles firmware. Okay? Så vi skal ikke snakke om firmware, men bare om hardware. Okay? Så vi skal starte med litt introduksjon på digitale systemer, og da vi skal snakke på transistorer i digital kretser, og da vi skal også sjekke hvordan man kan realisere digital kretser med CD4007, som det er en komponent, en elektronikkomponent. Ok, så la oss starte med power supply i digital systemer. Så hva vet vi om digital kretser? Vi kan starte for eksempel å analysere en klassisk eksempel av digital systemer som har PC eller computer. Som for en computer, dere har en power supply, så hvis dere bruker ikke power supply, computer funker ikke, ikke sant? Ok, laptop er batteri, ikke sant? Men en desktop uten power supply funker ikke. Ikke sant? Så det er veldig viktig at dette er det første regel på elektronikk, at hvis dere har ikke power supply, elektronikkretser funker ikke. Så vi trenger alltid power supply. It seems obvious eller intuitive at dere trenger power supply, men it happened mange ganger at studenter kommer til meg og glemte å slå på power supply, og kommer til meg og spør hvorfor elektronikkretser funker ikke. Ikke sant? Så det er beste ting at dere sjekker alltid hvis power supply er kablet med elektronikkretser. Så typisk i lab, første lab, studenter kommer til meg og spør meg hvorfor elektronikkretser funker ikke. Og første ting jeg forteller det at hvis dere slår på power supply. Og typisk dette er problemet. Så dere må sjekke det. Ok, så det er to typiske eksempler av power supply. For eksempel det er batteri som gir ut en konstant spenning. Og det er også PC power supply som transform oscillating-signal fra electric grid, så 220 volt, til en konstant signal. Vi kan for eksempel vurdere en batteri som en power supply. Hva skjer når vi slår på batteri? Batteri gir ut en konstant spenning. Så når vi kobler batteri til en digital krets, så jeg kaller det DC, jeg kan også, ja. Hva skjer er et batteri gir ut strømmen. Strømmen går inn digital krets, og da vi har et produkt mellom voltage, spenning og strømmen er power som power supply gir ut. Ikke sant? Typisk det er standard spenning på digital kretser. Vi skal kalle power supply. Vi skal bruke en symbol for power supply. Og symbol og label er VDD. Så når jeg snakker om VDD, jeg mener power supply. Typisk verdi for VDD er 1,2, 3,3, 5, 9 og 12 volt. Dere kan finne spenning, power supply spenning for en elektronisk krets på databladet av en digital krets. Som her er en eksempel av batteri som kables til en elektronisk kretser her. Det er veldig viktig at dere sjekker at jeg bruker to kabler for å kable batteri med digital kretser. Fordi batteri må gi ut en spenning, ikke sant? Og spenning det er en physical quantity som måles mellom to punkter. Så vi trenger to kabler. Ok, så når vi snakker med en digital krets, dette er schematic, eller vi må tegne dette schematic her for å representere en digital krets. Så en digital krets kan ha en input, en inngang, og en utgang, når en kan være 1, 2, 3, 4. Så dette er en generell digital krets, schematic. Men noen ganger det er veldig vanskelig å tegne en schematic for en digital krets, fordi vi har mange subsystems. For eksempel i dette eksempel, dere kan sjekke at vi har en power supply, da det er en større digital system, og inne digital system det er en clock generator, counter, allo, display, ja, det er masse subsystems. Og alle subsystem må kables med power supply. Så schematic er litt confusing, ikke sant? Så det er masse wire, masse kabler. Så beste ting at dere bruker symbols eller labels, fordi det lettere å forstå en schematic av en elektronikkkrets. Hvis dere bruker symbols eller labels, det lettere å forstå krets. Så her jeg må introdusere to veldig viktige symbol. En for VDD, en for GND. Så jeg skal bruke dette symbol her, og det betyr at dette symbol representerer positiv terminal av power supply. Men når jeg bruker dette symbol her, det betyr at det en negativ terminal power supply. Så jeg kan vise dere en eksempel. Så dette eksempel som jeg viste for. Til venstre side, det eksempel jeg viste for. Til høyre side, det det samme eksempel, men her jeg bruker symbols VDD og GND. Ok? Så du kan forstå at figur til høyre side, det lettere å forstå. Så dere må bruke labels når dere kan. Det bedre hvis dere gjør det. Så husk at wires eller networks som kables med symbols eller labels physically connected together. Ok? Det veldig viktig. Ok, så vi kan fortsette med neste ting. Har dere noen spørsmål? Det veldig viktig at hvis dere forstår ikke ting, dere gjør spørsmål. Eller hvis min norsk ikke så bra, det bedre hvis dere forteller meg. Ja. Så jeg kan skifte til engelsk, eller jeg kan gjenta det. Ja. Ok, så det ingen spørsmål. Supert, så vi kan fortsette det. Ok, så nå vi skal prøve å studere digital kretser som dere studerte på digital teknikk. For eksempel logic gates. Men vi skal prøve å studere det og beskrive det fra electrical point of view. Så her jeg tegner en not logic gate eller inverter. Men vi vet nå at alle elektroniske kretser trenger power supply. Så fra electrical point of view, det veldig viktig at dere tegner power supply connections. Så her jeg tegner connection mellom VDD og inverter logic gates. På digital kretser, dette ikke viktig, men i dette fag det viktig. Så når jeg slår på power supply, det skal være strømmen det går inn not logic gate, så logic gate kan funke, ikke sant? Hvis vi tegner ikke power supply, og hvis vi kobler ikke not logic gate med power supply, not logic gate funker ikke. Ok, så jeg håper at dere husker at når inngang av en inverter, eller not logic gate n, utgang like til 0. Når inngang 0, utgang like til 1. Men fra electric point of view, vi interessert å forstå hvordan man kan måle digitale signaler. Hvordan man kan måle 0 eller 1. Problemet at 0 eller 1 ikke en physical quantity. Så det ikke units. Så det ikke spenning eller strøm. Ikke sant? Så hvilke instrument jeg må bruke å måle det? Skal jeg bruke en voltmeter? Skal jeg bruke en amperometer? Skal jeg bruke en oscilloskop? Jeg vet ikke, fordi jeg vet ikke hvis det spenning eller strøm. Så vi må forstå hvis det hvordan vi kan måle det. Så Litt introduksjon til digitalsystemer og digitalsignaler. Digital elektronikkretser funker med digitalsignaler. Digital system jobber med binary system. En binary system bruker to verdier. Typisk vi kaller disse to verdier 1 og 0, men vi kan også kalle det lav og høy, eller vi kan kalle det også true eller false. Det er ikke viktig navn. Jeg er interessert på mening av disse navn. Jeg kan bruke også for eksempel hot and cold, black and white. Det er ikke viktig navn. Men det er veldig viktig at du forstår hvorfor vi bruker disse navn. Disse navn representerer motsatte things. Ikke sant? Så opposite quantities. For eksempel hot and cold. Hot er opposite motsatte cold. Ikke sant? High, det er opposite of low. Ja. Så det er veldig viktig at disse to verdier betyr motsatte things. Opposite things. Ok, så her er en eksempel av digitale systemer. La oss vurdere at vi har en digital krets som så vi vil bruke det å måle temperatur, og utgang av dette digital krets er en digital signal. Så når temperatur er større enn 30 degree, vi har et utgang er 1. Når temperatur er mindre enn 30 degree, utgang er 0. Så problemet her er at hvis vi vil realisere dette, lage dette krets, vi trenger en temperatursensor, vi trenger en elektronikksystemer som leser temperatursensor og gir ut en digital system. Men hvordan kan vi måle digital utgang? Så hvilke instrument skal vi bruke for å måle digital utgang? Fordi 1 og 0, det er ikke physical quantities. Så dere kan forstå at elektronikkretser, det er elektriske kretser. Så elektriske kretser gir ut elektriske signaler. Så utgang av en digital elektronikkretse må være en elektrisk signal. Så vi vet at det er to typer av signaler. Så det er spenning og strømmen. Og strøm. Og i dette fag vi bestemmer å representere 1 og 0 med strøm. Men det er også kretser som hvor strøm representerer 1 og 1. Men i dette fag vi skal representere 1 og 0 med strømsignaler. Det er veldig viktig. Fordi det er lettere...
Luca?
Ja.
Mener du ikke at vi skal... Eller det står at vi skal bruke spenningssignaler, er det ikke det det står?
Kan du gjenta det? Jeg kan høre ikke så bra.
Okay. Du sa at vi skulle bruke strømsignaler, men står det ikke at vi skal bruke spenning?
Nei, jeg beklager. Så vi skal bruke spenning, ikke strøm. Ja. Så vi skal bruke spenning, ikke strøm. Ja, beklager. Fordi når vi bruker spenning, det er lettere å forstå hvordan systemet funker. Ok, så når vi vet at utgang og inngang må være spenningssignaler. Så her i dette figur, jeg skrev V in og V out. Fordi jeg vet nå at inngang er en spenning, så V in, og utgang er en spenning, så V out. Ja. Hvis jeg i stedet bruker strømmen, jeg skulle skrive I in og I out. Men i dette fag, vi skal bruke spenning. Ok, nå vi vet vi må måle utgang som en spenning, så vi skal bruke en voltmeter. Men voltmeter er to utgang, en positiv og en negativ. Så det er lettere å forstå at positiv går til V-out, men hvordan man skal koble negativ terminal, negativ utgang av voltmeter. Så vi kan koble voltmeter i forskjellige måter, som jeg viste her. Men en av disse metoder er bedre enn andre. Og jeg skal vise det. Jeg skal fortelle the reason why. Ja. Så punkt som vi skal bestemme er punkt av kretset hvor vi skal koble voltmeter, negativ terminal av voltmeter. Vi skal kalle det reference node. Okay. Det kan være en punkt på krets. Vi kan bestemme det, men jeg skal vise dere at det er en punkt på kretset, det er bedre enn andre punkt. Ok. Men å forstå det, jeg må vise dette eksempelet her. I dette eksempelet, det er 3 digital kretser i parallell, og det er en power supply. Ja. Så hvordan kan vi bestemme referanspunkt eller på dette krets? Vi har 2 node, node A, node B. Så, ok. Dette del, jeg må beskrive det på engelsk, så kanskje det er bedre. You remember that it is quite easy to understand what is a reference point, eller referenspunkt. If you think about runners. Runners start all from the same point, starting point, which means all from the same reference point. So reference point and common point are synonym, so they mean the same thing. So my question is, spørsmål min er, hvor skal være referenspunkt på krets? Referenspunkt på krets skal være common punkt i krets. Jeg håper dere forstår det. So again, reference point means common point in many situations. Så for elektriske kretser, referenspunkt er common punkt på elektriske kretser. Så hvilke punkt er i common på elektriske kretser? Det er node A og node B. Disse to er common punkt på elektriske kretser. Så det er bedre å bestemme mellom disse to punkt. Så en av disse to punkt kan være en reference node for vår krets. Hvilke er det beste punkt? Node A eller node B? Beste punkt er node B. Jeg skal vise dere, jeg skal bevise dere at hvis dere bestemmer node B, da alle spenning på kretser er positiv. Og dette er veldig viktig på digitale elektroniske kretser. Så typisk, det er en convention at alle spenning på digital kretser er positiv. Så hvis vi vil det, vi må bestemme node B som reference node. Så nå dere vet at reference node må være node B. Men en ting det er veldig viktig. Når jeg snakker om node B, jeg mener en electric node. Så det betyr ikke dette punkt er. Kan du se min mouse pointer? Kanskje?
Ja, vi ser pointeren.
Ok. Så jeg mener ikke dette punkt her, men jeg mener dette del av kretset her. Hvis jeg har min padel bedre, men annotate. Det funker? Det funker. Ok, supert. Så dette er node B. Jeg kan også gjøre det. Så dette her. Eraser. Hvor er det nå? Ja. Så dette er electric node B. Ja. Fordi hvis du spenning in dette punkt her, i dette punkt her, i dette punkt her, i dette punkt her, i dette punkt her, er sammen. Ikke sant? Så det er sammen electric node. Ok? Så når jeg snakker om node, jeg mener electric node. Så dette er en node. Ok? En electric node. Ja. Så la oss fortsette. Man kan gjøre det sånn. Ok. Så da vi vet hvor er reference node av vår kretse, så det er her. Så vi kan koble negativ terminal av voltmeter til her. Men jeg kan også koble negativ terminal av voltmeter her. Eller her. Det er ikke viktig. Det er samme electrical node. Ikke sant? Så men det er bare viktig at det er bare viktig at negativ terminal av voltmeter koblet til en del av kretsen som koblet til negativ terminal av power supply. Så det betyr at dette punktet her, hva er spenning her? Det er spenning av negativ terminal av power supply. Sammen her, sammen her, sammen her, sammen her, sammen her. Så alle kabler som kables til negativ terminal av power supply er reference node. Ok? Der. Ja, hva er det? Ok. Sånn. Her. Ja, så nå vi vet hvordan vi kan koble en voltmeter på en digital elektronisk krets. Her er det positiv terminal, det er for eksempel på en utgang av digital krets 3. Og negativ terminal av voltmeter går til reference node av elektronisk krets. Spenning er vist på voltmeter er alltid positiv. Hvis dere måler en negativ spenning, det betyr at negativ terminal koblet til feilpunkt på elektronisk krets. Ok, så da vi kan komme tilbake til eksempel med inverter logic gate. Så hvis jeg vil måle utgangssignalet fra en not logic gate, jeg må bare bruke en voltmeter og kable positiv terminal av voltmeter til utgang av not logic gate og negativ terminal av voltmeter til reference node. Reference node er punkt av kretset som er kablet til negativ terminal av power supply. Det er veldig, veldig viktig. Ja. Så dere forstår også at utgangssignalet fra not logic gate er spenning mellom utgangsterminal av not logic gate og reference node. Ja. Samme regel er valid også når vi måler inngangssignaler. Så rød kable går til her, og svart kable her kobles her. Ja. Ja. Ok, nå jeg vil bevise at hvis du kobler voltmeter i dette måte, da voltmeter viser alltid en positiv verdi. Så, men for å gjøre det, jeg må introdusere en ting, så at vi skal diskutere bedre når vi kanskje på slide 100. Men det ikke viktig at dere forstår nå veldig bra hva skjer. Men jeg skal prøve å bevise det. Ok, så jeg må introdusere at alle digitalkretser laget av transistorer. Hva transistorer? Det ikke viktig nå, hvordan man kan how to fabricate it, how to realize it, det ikke viktig nå. Men dere må bare forstå nå at en transistor funker som en voltage control motstand. Hva en voltage control motstand? Det en motstand som verdi depend på inngangsspenning. Så for eksempel, hvis spenning V-in går opp, da verdi av dette motstand her går opp. Hvis spenning V-in går ned, da verdi av dette motstand går ned. Så dette en voltage control resistor, eller voltage control motstand. Så transistorer oppfører seg som en voltage controlled resistor. So behaves like a voltage controlled resistor. Ok, så dette en digital kretse når det noen transistorer. Jeg kaller det T1, T2, T3, T4, T5, T6. Og jeg bruker I use a symbol for the transistor, the voltage control resistor. Så i stedet for jeg bruker real symbol for en transistor, jeg bruker voltage control resistor symbol. Okay? Fordi vi vet at en transistor oppfører seg som en voltage control resistor. Ok, så det to inngang her. Vin A, Vin B. Og det en utgang V-out. Og det 6 transistorer. Og power supply 5 volt. Så hvis du kobler voltmeter med negativ terminal til referenspunkt, som her. Dette referenspunkt, ikke sant? Hvorfor det referenspunkt? Referensnode, fordi det kobler til negativ terminal av power supply. Så hvis jeg kobler negativ terminal av voltmeter til referensnode, og jeg kobler positiv terminal voltmeter til en arbitrary point på kretset, så her, eller her, eller her, eller her, dere skulle forstå at spenning positiv. Det veldig lett, det veldig enkelt å bevise det. Vi kan for eksempel fokusere her. Og vi kan fokusere på her. Dette side her. Så jeg skal prøve å bevise with some numbers. Ok, så vi vil for eksempel beregne utgangsspenning her. Så her. Og vi kan tro at verdi for transistor 5 det 1 kilom, og verdi for transistor T6 det 10 kilom. Okay? Så T5 oppfører seg som en motstand med 1 kilom verdi, og transistor 6 oppfører seg som en motstand med 10 kilom verdi. Så her Jeg håper at dere kan beregne V-out fra elektriske kretser. Dette er en spenningdeler, ikke sant? Så formel for spenningdeler er dette her. Så hvis vi skriver her 10 kilom. My God, so ugly.
Luka,
Ja.
hva er greia med de pilene som peker på resistorene, liksom?
Jeg hører deg veldig, veldig dårlig. Kan du gjenta det? Beklager.
Ja, hva er greia med de pilene som peker på motstanderne? Motstanderne, er det sånn å si? Ja.
Ja, kanskje det er bedre hvis du skriver på chat. Det er bedre. Kan du skrive det på chat?
De pilene er bare at det er en variabel motstand, er det ikke det?
Ja. Ja.
Det er variable motstander.
Så dette er variabel motstander, dette er variabel motstander, dette er variabel motstander, og dette er dette her.
Men hvorfor, altså, over T4 da, så går den streken ut, og så til T5 og T6. Hvorfor er det vist på den måten?
Ja, jeg bare... Ok. Hvis spørsmål er hvorfor jeg bestemte 1 kilom eller 10 kilom?
Nei, det er ikke det.
Kan du gjenta det?
Nei, det er ikke så farlig, vi får lære det sikkert senere.
De motstandene er variable i forhold til spenningen som går inn på V1A og V1B og så videre.
Og det er ikke...
Pilene bestemmes av spenningen.
Den
Den variable motstanden er jo spenningen, ender seg i forhold til spenningen inn. Altså den spenningen som går ut av T2 er jo den spenningen som går inn på T5 og T6.
Ja, så det skal være en minutt, så det er... Hvor er det? Det skal være en spenning her. Og verdi av T5 og T6 depend av spenning her. Men vi bare gjør nå en eksempel. For eksempel hvis spenning er 2 volt. Det er ikke viktig. Og vi også tror at spenning verdier her er 1 kilom og 10 kilom. Ok, jeg kan sjekke på chat. Så. Ok. Så det er ikke viktig. Dere kan velge en verdi at dere vil. So you can choose a value that you want. Regardless which value you will use, it will always become positive. So you can try by your own. It's not very important. Det er ikke viktig.
Luca, should we take a break and then continue afterward?
Yes, we can take a break now. I will just, let me see 1 second.
And I've asked several of the students in the class if we should continue in English, and they're all positive to that. So if you want, you can continue next hour on English.
Yeah, for my det er det samme. So for me it's the same if you understand better, if you understand in Norwegian, for me it's okay. But again, as I said, explanation in English definitely is for me.
Yeah,
better.
but you can take the next hour of the session. You can take it in English, and then we can decide what's the best for us. If
Yes,
it's okay for you.
I think it could be a good way to do like that. So
Yeah.
you can compare. Okay.
Yeah. Okay.
So
Thank you.
let's take a break, and then how much break you do usually? I 10 minutes, 5 minutes, I don't know.
10 minutes, perhaps.
Okay, great. Okay, so 11:15 we are back.
Okay, thank you. I will put the recording on pause in the meanwhile.
Yeah, super. I had some problem with Canvas with what is called media site, which is the part that was suggested to us for using it. For some reason, doesn't upload 2 GB of things.
That's a lot, though. So
yeah.
I get it. Yeah.
So I think I create just now 1 channel in YouTube, and hopefully it seems now it went through. It's still not link available in Canvas, but hopefully for today I will place it. The video again are not real-time videos, so it's video that I do in my office, and I try to provide all the information I maybe was not able to provide in the class. So I try if now we'll proceed in English, I will try to cover everything I can. So in that case, maybe the video is just a repetition, but if I don't have time, then there you can find all the information I wasn't able to go through.
Yeah, and also, I mean, it kind of makes it easier in case somebody can't really be
Great.
like
Yeah.
here, right? I
Yeah,
mean, like
yeah.
Katinka, for example, she has another class at the same
Yeah,
time.
yeah. I did this one also for that reason. Last year, many students, they actually were asking for this video because someone, they couldn't come. And then this year, I definitely willing to do that. So again, if you have any feedback about the course, please give it to me during the course. I'm very welcome, and I try to improve the course every
Oh, no.
year. So
I think we'll just like leave hate comments on your YouTube video. You
that would be.
suck and all of that.
Then I cannot earn money. Then I think so. That's aside the purpose of the channel. Okay, but anyway, let's start again. I think if all of you don't have any other question, I will proceed then with the other part of the. Can you see my slide?
Yep.
Okay. Okay, I will proceed then in English for the next part. Again, I've been told that sometimes I go too fast, so please tell me to slow down if that is necessary. Okay, so this is not the slide, of course, that I need here. Okay, as I was saying before, it is very important to understand what is the reference node in an electronic circuit. And from now on, you know that the reference node is the part of the circuit which is connected to the negative terminal of the power supply. In digital electronic circuits, this is the main rule. We will see in analog circuit, we have to add a few information. In this circuit here, again, I wanted to prove that the voltage with a voltmeter measured in any point of the circuit is always positive. I hope you remember the voltage divider formula, spending Dollar formula, which is this one here. In this example, I'm just assuming and guessing that these two value of resistor have 1 kilo and 10 kilo, regardless what is the voltage here. It can be 2 volt, 1 volt, 3 volt, it doesn't really matter. It's not important at the moment what is the voltage here. And this voltage here does not affect this part of the circuit here. So the voltage I have here will not affect the voltage I have here. This is just a spending Dollar here. Will this voltage here at the input will just affect the value of the resistance of the Mustang. Yeah, how to erase here? Okay, so you can try by your own and prove yourself that wherever you are measuring the voltage is always positive. It's not difficult. And I also try to do it with just a little example here. Okay, so let's proceed. So again, the voltage measured in digital circuit is always positive if measured between the reference terminal and any point of the circuit. Okay, another thing that is very important is that what happens if I connect the red terminal, the positive terminal of the voltmeter, in the same point of the reference terminal? In that case, you understand that there is no voltage difference or electric potential difference between the 2 points here. Therefore, the voltage you see is 0. So this is wrong. The voltage here is 0. This make think many times the electronic engineer that the voltage in this reference node is 0 volt. This is actually okay if you think in these terms. So if you think that the negative terminal is here and the positive terminal of the voltmeter is here, but say that the voltage in this point, the electric potential in this point is 0, this is not totally correct, unless you use the voltmeter as I show in this example. This is something we will go through again a little more in detail. If you wish, as an artifact or as a way to make it easier, your way to think, you can think that this is 0 volt in your mind to make it easier, but in the real life, in the real electronic field, I'll say this is not really 0 volt. and I will prove you later on. But when you use a voltmeter, then you can think that if you connect the red point here and the black point here, then it's 0 volt. I will use to you this kind of like way to think in the practical exercise. So don't worry. If now is a little confusing, then it's not a big deal. With example, then you will understand better. Okay, so another thing, because if we measure with the red terminal and the black terminal here is 0 volt, it shows 0 volt. We are usually thinking that the voltage there is 0 volt. And but usually again, in electrical field, we say that 0 volt is actually the ground. So the earth, the real ground, the physical ground, that is really 0 volt. Although that is, again, from physics point of view, is not definitely totally correct. But we like to think that that is 0 volt. So then if you think about it, if that is 0 volt, then this point here cannot be 0 volt. So, but this is just to tell you that in digital circuit, if you like to think this one to be 0 volt, then you can call this one ground, although they have, again, different meaning. So to summarize, I know that this kind of explanation may have maybe confused you a little, but it's just to say that if you want, you can call this negative terminal here ground. Is another name that is commonly used for the reference node. If a physics teacher or professor listen to tell you that this is 0 volt, he will tell you it's wrong, and I mention it to you. But again, as an electronic engineer, we like to think about that way. But it's also good that you know the reality. So we will go through again. Okay, we still have not done yet. We have to understand how 1 and 0 are represented. We know there are voltages, but we don't know which value, right? We remember that you have to think just that 1 and 0, I said before, represent two opposite things, and they must be electrical voltage. So what are the opposite voltage in a digital electrical circuit that you can find, for example, in this circuit here? Well, we just say that if I measure, for example, in this situation here, I measure 0. If I measure with the red terminal here, in this point here, so if I connect like this the positive terminal, then I measure VDD. And you can also prove your own that there is no voltage greater than VDD, right, in the circuit, which is 5 volt in the case. So this means, if you think very well, that the two extreme voltage in a digital circuit are VDD and 0 volt. So it makes sense to choose to represent 1 and 0 with the minimum and the maximum voltage in a digital system. Why? Because I said that 1 and 0, or hot and cold, or true and false, has to represent opposite things. And maximum and minimum voltage in digital system are opposite things, because maximum is opposite the minimum, right? And what are the maximum and minimum voltage in a circuit? I just said that are VDD and 0 volt. So we use VDD and 0 volt to represent 1 and 0, okay? I hope that this kind of like way to explain it, you understood it. So we use VDD and 0 volt because they are the maximum and the minimum voltage in a circuit, and maximum and minimum are opposite, and we know that 1 and 0 should represent opposite things. Okay, finally, I'm just now here again drawing the inverter logic gate from electrical point of view and using all the concept that I just explained. So I wrote V in, V out, because they are voltage. I connected to the power supply, but instead to show the connection to the battery, I put the symbols, okay? I put the symbols for VDD, I put the symbol for ground, which means that here the inverter is connected to a positive terminal of power supply, and here is connected to a negative terminal of a power supply. Next. Now let's have a look about the inverter logic gate from electrical point of view. Okay. In parentheses here, you have the behavior of the logic gate from digital point of view, logic point of view, which you'll study in digital technique. Instead, over there, you have the electrical point of view of what happened. So when the input is 1, the output should be 0. But we know now that when the input is 1, means that the input is VDD. The voltage at the input is VDD. When the input is VDD, the output should be 0, which means 0 volt. Now you understand that when the input is 0 volt or logic 0, the output should be VDD. This is the electrical interpretation of how not logic gate work. Now, what happens if you want, for example, represent a varying signal, so a signal that changes in time at the input, and you want to measure what is the output, the change in time, right? For example, what if the input is 1 0 1 0 1 0 1 0 1 0? So change in time, it oscillates between 1 0. So again, what we have to do is just create a signal with a device which is called signal generator, which create 1 0 1 0. And we know that 1 0 1 0 means VDD is 0 volt, VDD is 0 volt. So this signal generator will create a signal which oscillates between VDD and 0 volt, VDD and 0 volt, VDD. So if VDD, for example, is 5 volt, then you have a signal which is oscillating between 5 volt, 0 volt, 5 volt, 0 volt, 5 volt, 0 volt. What is the waveform that really represent this oscillation? Is a square wave. So we keep 5 volt for a certain time, then we create 0 for a certain time. We have 5 volt for a certain time. We have 0 volt. So if you think very well, this is nothing else than a square wave, as I represented here. So we have 0 volt for here. This represents 0. 5 volt for another interval of time. This represents 1. 0 volt for another. Okay. So in conclusion, is easy to understand that digital signal, most of the digital signal are represented electrically with square wave. Okay. And it's important that you know that the square wave value, the square wave, oscillate between 0 volt and VDD. So this is the representation from electrical point of view of a digital signal that change in time at the input. So in the top plot, you can see the digital input that change in time. And in the bottom plot, you see the digital output that change in time. And you can really see actually the output voltage here by using the oscilloscope, which you will do in the lab, hopefully. Okay, let's go in the next topic, which is, let's go finally to understand, to introduce the transistor little by little. Let's go to have a look about what is inside of a digital system. I will start with a simple example that I hope that everyone knows, which is how computer works, what is inside a computer, and how are they able to perform their operation. Again, if you have any question about the previous part, please ask. Otherwise, I will proceed. Okay, no question, I suppose. Don't feel shy again, and there is no wrong answer. Yeah, let's say that, yeah. Okay, so calculator or computer is doing calculations, so it's the processing of data and so on. This one, everyone, I hope we know. And a computer is practically an electronic device and is made by electrical components. Which electrical component are inside of the computer? I think most of you already know them, but let's analyze the structure of a PC, for example. But this analysis we are doing is also correct for any other digital circuit. I'm going to show you an analysis of a computer, which is the same analysis that people usually do when they analyze how the human body is made. So you have the human being made is an organism, right? So there are organs inside. There is a group of organs inside. Organs are made of tissue are made of cells, and so on, right? We are going to explore little by little the smallest part of the human body. And the same things I will do it now. So a computer is made by boards, like the motherboard, the video card, and so on. The boards are made by integrated circuit, like a CPU, memory RAM, and so on. Inside of a memory RAM, you can find register, multiplexer, something that you should be already remembering from digital technique. And inside of register and multiplexer, you have logic gates. But then you stop there at digital technique, maybe. You did not maybe go too much in detail about what is inside of digital gates. So how do we actually build logic gates? Because in the end, in digital technique, you didn't need, because you just program FPGA, and you just write a bunch of code and then everything works. Here instead, we're going to look into how we actually build this. So in some way you can think what is the minimum element inside of FPGA in some way. So here is just a representation of what I've just said. So we are going to look about what is a transistor. So inside of logic gates, you already know there is a transistor. Finally, let's go to have a look what is a transistor. Now I will introduce again a few concepts that I hope most of you remember. If you don't, then again, look about the digital circuit book and you have to review them. I won't go in detail here. I don't have time today. So then you have to look about your own. So you know there are different logic gates. Different logic gates are represented by symbols. There is truth of table, which represent how they actually work, what is their job to do. So we have in one column the input and the other one in the output. The column which is indicated with X is the output. And the A and B, they are the input. So not and, or, nor, XOR, and XNOR. Yeah, so how do we realize logic gates? Which electric component are we going to use? We know we use transistor. And what I want to teach you in this part is, and also what I want to teach you during all this course, is that you understand the method. This course is not about memorizing things, but is a course where you have to understand the procedure and the method. Once you understood that, you're able to solve any type of electronic circuit that you will have to solve. Okay, I want to start then to try to understand how to build these logic gates by the simplest example that we can use, which is the NOT logic gate. Now, we already seen how this work and the logic gate work. So we have VDD at the input, 0 volt is the output. Again, in this course, I try to talk more from electrical point of view. So I talk about VDD and 0 volt. I don't talk anymore about 1 and 0. We have to start to look about this device as electrical component. So when the input is VDD, the output is 0 volt. When the input is 0 volt, the output is VDD. How do we implement this? If you think about it, and I will show you soon why, this device can be easily realized by using switches. Just for you, a little review about switch. If you don't know what it is, a switch from electrical point of view, a switch is a device which can assume two states. One is open, one is closed. Is an open switch when current cannot go through it, is a closed switch when current goes through it. For some of you, can be a little, I know from a previous student, can be a little, there can be some misunderstanding because some of you, when you think about open, think about on, or think about something that is, let's say, let pass things. And when you think about close, think about off in some way. So it's the opposite logic. The reason why I say open, so the reason why this one is open and this one is closed is because, again, it's related to the current. So if the current cannot pass through, this kind of component behave like an open circuit. That's why it's called open switch. If the current can go through, you know that this the voltage between these 2 points here, between this point A and the point B, is 0 volt because they have the same electrical potential. This means that this closed switch behave like a short circuit or a closed circuit. So remember that the other two names of open switch and closed switch could be also open circuit and short circuit. Or in other words, I can say that an open switch behave like an open circuit and a closed switch behave like a short circuit. Okay. I hope that the short circuit, open circuit, you have already learned from LELC. I don't put my hope too high, but I hope that some things you have learned there. Not for your fault, but I know that is, I think, in my opinion, that the curriculum in that course is a little too much small, but okay, my opinion. Anyway, the digital circuit that I just showed before, which is the inverter, can be actually realized by using a switch, which can be or closed or open or closed. Yeah. We say that the switch is off when it's open, and we say that the switch is on when it's closed. Let's see how to use the switch for implementing the inverter logic gates. So when the input is VDD, I'm talking about this part here, we know that the output should be 0. And with the switch is very simple, because now if I connect the ground, which we said we can think to be at 0 volt, we can connect the ground with the output with a closed switch while the other is open, okay? Then it means that the voltage here in this point is the same of the voltage here, which means 0 volt. In the other case, when 0 volt is at the input, you want that the output is at VDD. And this one can be achieved if we have a closed switch here and an open switch here, because the potential here in this point is the same as the potential, electric potential here, because they are connected, right? Okay, so you understand now very easily that I hope that an inverter logic gate can be realized very well with switches. So these switches should open and close depend on the value at the input voltage, of course. You can see in this situation here, in this one here, the top switch should be open, the bottom is closed, with the same input. So here we need to switch that behave in opposite way, right? With the same input. So probably this input control these two switch. So the same voltage control the two switch, but the result is different. One is open, one is off. So they can't behave in opposite way, right? The same here. Yeah, the input is 0. This voltage control the switches, but one is on, the other one is off in the opposite way. So in some way, these two types of switches has to be opposite in behavior. Anyway, what I want to say with this is that we are talking about a voltage control switch, because the state of the switch depends on the input voltage. So depend on the input voltage value, you change the state of the switch. Do you remember any input voltage switch? I hope that you have worked with those, or maybe some of you have worked with those, maybe those ones that do el auto. You may have worked with PLC in digital technique. I hope, if the curriculum is still the same. Inside of PLC, there are some device sometimes called relay, and relay is kind of an example of let me remove here, of a voltage controller switch. So depend on the voltage in these two terminals, which I call control terminals, you can close or open here the switch. So here, just for those one that had never seen, I hope that here there should be a video. Here, okay. So here is open. I apply voltage here, and the switch is closing, and the lamp turn on, because now you have a power supply here. The current can flow through the lamp, and the current can then go back here, right? The two parts, so this circuit here and this circuit here, they are not connected electrically, but this circuit here control the state of the switch. Okay, this is not very important actually to know how it works a relay. Relay is not really the main concern in our circuit. Why? Because the relay are usually huge, are very big. And the hubs that are electronic, as you know, electronic engineers try to make devices very small, always smaller, smaller, and smaller. So working with a relay which is huge is definitely something we don't like. So we have to find another device which works like a relay, but actually is not a relay. And the best candidate for this is a transistor. I want to point it out again. One thing that is very important is that the two switches, the top switch and the bottom switch that you see here in this inverter, in this what is working as an inverter, should work in opposite way, because again, for the same input, they have different state. One is off, one is on. Okay, so it's important that to realize this device, it's important you understand you need two different types of switch. Both they are switch, but opposite behavior. When you have opposite things, we usually in electronics say complementary. So when you say that, for example, you have a friend, you are a good person, your friend is a bad person, you are complementary because you're good, the other is bad. So complementary means kind of like you complement, like yin and yang in Chinese culture. I don't know. I hope that you understood anyway. So complementary are two things that complement each other. So we need one device which can be of two type, and the two type work in complementary way. Okay. So we need, in a few words, transistors, but we need two type of transistor that behave in complementary way. Here we are, finally. There is something that maybe can make you a little confused now, because now I want to introduce transistor, right? But at the very beginning of the previous slide, I say that the transistor behave as a variable resistor. And then I'm saying that I need a voltage controlled switch. So it seems that, so does transistor is a voltage controlled resistor or is a voltage controlled switch? So it seems I'm saying kind of different things, and this one can make you confused, could make you confused. But again, this is due to the fact that these two models, voltage controlled switch and voltage controlled resistor, are two different point of view of the same device. And I will show you why, and I will show you that these two actually model, they are related. Okay. I want to then start with the model that I started with to represent a transistor. So a transistor is a three-terminal device, which I call A and B and control signal. Okay. And again, I want to start with the same thing that I started at the very beginning, saying that the transistor works as a voltage controlled resistor. Okay. So until here, everyone we knew about it, I hope. So as I said before, depend on the voltage here, which I call the VCTRL, the equivalent resistance of the transistor change. But again, I need two type of different transistor, now I know, to implement the inverter. One with high input voltage should have, for example, low resistance, and with low voltage should have high resistance. The other should behave in opposite way. Okay. So what I know again at the moment is that I need a transistor. Transistor is a three-terminal device. Transistor is a voltage controlled resistor. And I need two type of them, and they have to behave in different way, in opposite way or complementary way. So since it's a voltage resistor, I can say a voltage controlled resistor. I can say that one transistor has high resistance when the voltage input voltage is low, and low resistance when the voltage is high, what is written T1, and the other should behave in the opposite way. Now let's see if I use this kind of device to implement an inverter, if the system work or not. Now, T1 is the bottom transistor, and T2 is the top transistor. And here in the bottom, you have the behavior of these transistors. So if the input is VDD, then the bottom transistor T1, you can see under, should be high resistance or low resistance? Should be low resistance, because I say when VCTRL is high, then the resistance should be low. So the resistance of the transistor T1 should be low when the input of this device is VDD. And here I wrote 1 ohm, for example, right? It's just an example of number, just to put some number. When the input here is VDD, then the voltage control of this T2 is VDD. Then I go to T2. Voltage control is VDD, so it's very high. We say that one logic value or high logic value means VDD. So when the gate control voltage of T2 is high or VDD, then the resistance should be high. Yeah, very ugly here. Okay. And for this reason, I can say, for example, that T2 is equal to 1 mega ohm. Now, if I solve the voltage divider, as I showed you before in the previous circuit, you can see that the voltage that you calculate is very, very small. Okay. Approximately 0. Okay. And this is actually what I want, Because if this one here, if the circuit here represents an inverter, when the input is VDD, the output should be 0 volt. So by using this model here, I achieved what I want, at least for this part of the inverter. Now, if I repeat the same operation or way to think for all of these other parts, you can prove the same. So when the input voltage is 0 volt, T1, so the control voltage of T1 is low, so T1 is equal to an high resistance. So here I have to write 1 mega. When the input voltage is 0 volt, the control voltage of T2 is low, is very low. So the resistance, equivalent resistance of T2 is high, is low. Sorry, yeah, this is, I was confusing myself. Is low. Yeah. So where the control voltage is low, which is this, then there is the equivalent resistance is low. So here I put 1 ohm. Now, if you do the voltage divider here formulas, you get again, you get VDD, which is actually what we want, because when we have from an inverter, when we have 0 volt at the input, we want VDD at the output. So this model here, modeling transistor as resistor, it works if they behave like this. But now I want to, so now you know that the model of the voltage control resistor work, but I showed you before that the model of the switch also work. So which model should I use? Are they different model or not? Actually, if you think very well, the two models for this specific case here, they coincide. Why? Because when you have VDD, maybe I have another slide here. Yeah. When, okay, let me remove here. So the two models, I want to prove that they coincide. In fact, when I have the input VDD, I say that T1 is low resistance and T2 is high resistance. Instead, when I use the model switch, I say that the top switch should be off and the bottom switch should be on. If you understand, these are these two models, maybe I can highlight a little, they represent the same things. Why? Because when the resistance has very high value, you can think that the current that goes through that resistance is very, very small. So that a very high resistance, it behaves approximately like an open circuit. But an open circuit is nothing else than an open switch. Okay, so this resistor here that have very high value, it behaves like an open switch because the current that passes through is practically almost zero. It's very small. So here instead, the resistor T1 is very small, and this means that the voltage across this resistance is almost zero. And as I said before, if the voltage across the device is almost zero, it behaves like a short circuit, which means a closed switch. So you understand that the model that I choose for the transistor, which is the initial one with the resistive voltage control. I hate these things. Okay. The model I choose for the voltage control resistor, it practically match with the voltage control switch model that I presented too. So the two, they are coincident. So it's good to say that the transistor is a voltage control resistor if the behavior is this one here that I described before, because it coincides the same of the behavior of a switch. Now, when we are going to analyze the next circuit, since you know that a transistor, which is better represented by the voltage resistor model, okay, behaves nothing else than a switch, which is much easier to understand, we are going to consider the transistor just like a switch. So my point is that, yes, the transistor is better modeled by the voltage controlled resistor model, but is much easier to understand how the transistor behave if we use the switch model. Okay, so from now on, you know that the model that we're going to use for working with transistor is the switch model. Okay, yeah, this is the summary of what I just said. Okay, again, we will proceed our analysis by assuming that transistor behave like switches or better voltage controller switches, because we say that is equivalent to consider it as a voltage controlled resistor. Okay, but think about a switch is much easier, right, than a resistor. Okay, so finally, let's give a little more information about the transistor. There are two types of transistors that exist in electronic. Actually, there are more, but the one that you have to be concerned about, there are two. One is called bipolar junction transistor. The other is called metal oxide semiconductor field effect transistor. In short, the first type is called BJT. The second type is called MOSFET. In this course, I want to focus only on MOSFET. Why? Because all the modern electronic circuits focus on MOSFET, are made of MOSFET. As I said before, we need two switches that work in different way. This is why when they invent MOSFET, they also invent two different types. One is called PMOS and the other is called NMOS. These two transistors, these two MOSFET, they behave in opposite way as we want. And you can again think a transistor like a switch. Then we just said a MOSFET is a transistor, so a MOSFET is a switch, right? Then there are two types of MOSFET, PMOS and NMOS. So it means that PMOS and NMOS, they will behave, of course, as switches. And again, they will behave as opposite or complementary switches. These are the symbols for NMOS and PMOS. Transistor, these are the symbol for the PMOS. This is the symbol for the NMOS. There is something a little strange here that you should already notice, is that we said that until now the transistors are 3 terminal, but here there are 4. This is very strange. But I will show you again that there is a trick here behind. Okay, but for the moment, just take in consideration that the symbol has 4 terminals: gate, source, drain, and bulk. The same name are used for the PMOS and the NMOS. The main difference here you can see is the arrow. So it's very, for someone, difficult to discriminate them because you have to remember the direction of the arrow. But I will show you that in digital electronic, this one is actually not important. And I will show you why. Yeah, as I wrote here. But in analog electronic, you will see when we go to design amplifier, this is very important. Why in digital electronic is not important, this 4 terminal, which is called bulk? Well, the point is that in digital electronic, in any digital electronic, the bulk is always connects to fixed points. The bulk of a PMOS is always connected to the VDD terminal. The bulk of the NMOS is always connected to the ground terminal. This is a rule. It has to be like that, and it will be always like that forever and ever. So you understand that if you remember this rule, there is actually no need to draw the 4 terminal. I mean, you know that when you build a circuit, you are going to connect to VDD, the bulk of PMOS, and the bulk of the NMOS. But in order to not make complicated the drawing, the schematic, because remember where is the arrow here, the direction of the arrow might be a little tricky for some of you. You don't need actually to draw the bulk terminal, because again, we know where it should be connected. It's implicit, okay?
Luca, a short question.
Yeah.
Is it wrong of us to think of them like positive and negative, like PMOS is positive connected to the VDD and NMOS is negative connected to the reference? Is that wrong to consider?
It's not something I would encourage to think about it, because in real P and N does not really mean in some way positive and yeah. So it's something that also can lead you to some misunderstanding later on. So I don't suggest that. Some people I know, they might think about that. In this course, I not encourage you to do that. Yeah.
Okay, thank you.
Later on, probably it will be also more clear the reason why. But okay, so just proceeding very fast. So if I don't draw the bulk symbol, then you can see in the right side, how do they discriminate them? They look the same, right? So electronic digital engineers thought, okay, we have to anyway discriminate them. We have to find an easy way to do it. We don't like the arrow. So to do that, we just add one ball, one circle at the input gate of the PMOS. In this way, I know which is the PMOS and which is the NMOS. And I don't need to draw the gate, the bulk terminal, okay? So from now on, the symbol in digital electronic of a PMOS is this one with the circle at the gate. The one at the NMOS instead is without. Okay, just looking about how much it means. Yeah, I would like to arrive at least at slide 107, so I conclude this this topic, if you allow me. Okay, so let's have a look a little more in detail how this transistor MOSFET work. The NMOS and the PMOS again has to work in opposite way, and now we are going to understand better why. When we have a voltage between gate and source, I'm talking now about the NMOS, okay, so I'm focusing on NMOS. When the voltage between gate and source of this device is VDD, then the connection between source and drain behaves like a short circuit or closed switch. When the voltage between gate and source is 0 volt, so the voltage between gate and source is this one here. I don't know how you like to, very ugly, yes, okay. And when the voltage gate source is 0, then the circuit is open, or on open switch. So there is, you can imagine that there is an open switch between drain and source. In the opposite way, for the PMOS, when you have the gate, the source gate voltage, be very careful. Here is source gate voltage, here is gate source. When the source gate voltage is VDD, then this is open circuit, and then when here is instead 0, this is a short circuit. I think actually I did, yes, okay. Okay, so this one is okay. In digital electronic, is not very important actually to know what is the source voltage at the transistor. Here, there should be a very long discussion about it, but you have to just take this for granted for the moment. So for this reason, the condition that I wrote before, they can written again without the source voltage, okay? But you have to understand what does it mean, okay? So I will try to emphasize these things. So saying that VG is equal VDD, as probably you should have understand now, it means that the voltage between gate and the reference voltage, the reference node, is VDD. So when I say VG equal VDD, I'm saying that the voltage between gate and this ground terminal is VDD. So when the voltage between gate terminal and the ground and the reference node is VDD, then this one is short circuit. When the voltage of the gate is equal 0, so between the gate terminal and ground, this is an open circuit, and so on, okay? So you can write this condition that I showed before, which look kind of complicated because you have to take into account the source voltage. So if you, in digital electronic, that is not necessary. So you can just focus on the gate voltage. So these are mainly the condition that you have to look about it. So the previous slide was just to show you what are actually the condition from electrical point of view. Digital electronic have some tricks which simplify your life, and these are actually what you have to look into. Okay, now we are finished soon. We know that we have PMOS and NMOS. They work in complementary way, which means opposite way. All the digital circuit which contain PMOS and NMOS are called Cmos circuit, where the C means complementary. Okay, so when I talk about Cmos circuit, there must be one PMOS at least and one NMOS. Okay. Now, very briefly, if you think about this opening and closing switch here behavior that we have analyzed before, and if you compare it with this closing and open switch of this transistor, this I hope you can do it at home or by your own anyway, you can understand that we can substitute the top switch here with a PMOS and substitute the bottom switch with an NMOS. And the circuit will behave exactly like this, exactly as they are voltage controlled switch, in this exactly way. Okay. So when the input is VDD, okay, then what is the state of the PMOS? We are going to look about the table here. We are going to look about PMOS. You see VG equal VDD, then is an open circuit, which means off. In fact, here the PMOS is off. When the input is VDD and the VDD is at the gate of the NMOS, which is the bottom, then we are going to watch the table. The VG is VDD, and you can see that the NMOS behave like a short circuit. So it means on. And here indeed is on. So if the NMOS is on, which behave like a short circuit, as shown here in the right, and the PMOS is off, which behave like an open circuit, which means is off, then the output voltage is 0 volt, because the NMOS connected the output terminal directly to the ground, which we say we can think about 0 volt. So the potential here at the output and the potential at the ground should be the same, because they are connected together. So the output is 0 volt, as we want, because when the input is VDD, the output is 0 volt, as an inverter should do. The same for the bottom part. I just go through it very fast. So when the input is 0 volt, the output has to be VDD. This is correct, because when the gate voltage of the PMOS is 0 volt, we're going to look about the table. This PMOS, gate is 0 volt, then is a short circuit, which means on. In fact, here is on. When the gate of the NMOS is 0 volt, let's go to watch about the table. Should be an open circuit, means off. This is off. And here is the equivalent switch circuit. And if you look about the equivalent switch circuit, because it's always very easy to think about the transistor as a switch, then you can understand that the output terminal voltage is the same of VDD. Okay, so I think for today, then this is all the things I want to go through. We don't have, actually the next part is the most difficult. So please have a look about the slides. I will try, I think they are already uploaded in Canvas. Go through the slide before next time, because next time we are going to use the knowledge that I teach you today. So if you did not understand those, then it will be very difficult to understand what's will going on next time. If you have any question, please feel free to ask now. I will be very welcome to answer to your question.
I have a question.
Yeah.
Is this the same as PNP and NPN?
Yes, BJT are two different type. There are two different type of bipolar transistor, which are NPN and PNP, which work in a similar way of this MOSFET, PMOS, and NMOS. However, there are some things that more tricky there, which that's also another reason why I don't want to go to BJT. But the main reason why I don't explain BJT in this course is because no one mainly uses it anymore in digital circuits, but they use mainly MOSFET. So I want that you have very good understanding about what actually modern circuit is. I don't see any purpose to explain what is actually is old, and it would be just a little probably taking my time on doing that and steal time from the MOSFET, which is actually I think is most important. But definitely there are many documents in internet about the NPN and PNP, and the working principle is similar. You might again see a little more tricky things there. So in my opinion, leave that part, don't look about it. You will have nightmare in the night, so don't do that. Yeah. Any question?
Are we actually going to learn
Are we
about,
going to
learn about like
use
what
or
the
check the PowerPoint ourselves,
okay.
or are we going through
Yeah.
it the next lesson?
Okay, sorry. I first maybe Marianne and then maybe Amanda later. Can you repeat? Sorry, Marianne.
Sorry. Are we going through this the next lesson, or are we going through it ourselves?
The part 2, which is the one that is written transistor and digital circuit, is the one that I will go through next lesson, because I plan to lecture for digital circuit. And actually we arrived to a good point here. So in the next lecture, I will go through this complicated part that I hope you can see now, which use transistor to build logic gates and complicated electronic circuit. So we will go together through it, because we had actually done quite a lot today. So yeah, so I hope I answered to your question. Yeah. But all the previous part that I explained today, you should look into it by your own. I mean, review it and so on. If you have any question, feel free to send me email. If you did not understand something about the slides, send me an email, or we can just contact me. We can have also Zoom one-to-one meeting. It's not a big deal for me. You can also come to my office. My office G331. Feel free to come if you think you want a one-on-one explanation. I'm available in any way. So I think Amanda has a question?
Yeah. When are you going to know if it's going to be a physical or a digital class next Monday?
I was saying before that no, I think that maybe like this is the way that I would like to proceed for the moment. I don't know. I think that now that you saw how it is in the Zoom, you can also maybe give me your feedback about what you think about in Zoom. Again, I'm talking with the colleagues, and most of us are a little concerned about the situation that might become in these following weeks, due to the fact that many people come from the ferie, and most
And they were
of
partying.
students,
Yeah.
yes. So again, it is a little concerning. So I think for me, the Zoom lecture, at least for the moment, it worked, but just because in the slide, this one was very descriptive way of the part of the course. So I don't have to show you how to solve the circuit. Of course, later on, there will be part where I have to show how to solve the circuit. This morning, I had some problem with the pad. So if this problem with the pad, I cannot solve it, or there will be more problems, then I think I can definitely come on physically there. I definitely would like to do it physically, but again, there is a little concern between us, and I will try to evaluate that. For me, again, I also told you, I think from the very beginning, if I can do it physically, I definitely prefer, but let's see how it goes. I hope for you is not very big deal for the moment, but again, let me have your feedback. I'm always very welcome to hear from you what you think about it. Yeah.
So far, it's been really nice. Are we actually going to get into the physics of the MOSFET, like transistor, like like how it actually works and how the voltage actually disperses itself or whatnot?
The course, in theory, yes, it is expected to do that. At the moment, I did not do that because it is not the main concern for you to understand what physically happens inside the transistor to make it work like that. I think it's better before you understand how the device behaves as a component, and then we are going to understand why all of these things, how all of these things happen. But to do that, again, I will tell you before that lecture, you need to remember physics concepts, which I don't know actually if you have done, because recently everything is changing. But I can already mention we will need electric field, magnetic field, electrons. What are electrons? How do they move? Also from mechanical physics, you need to know what is at least mass per acceleration equal force, and the Newton's law. All of the things, you need to know them. So please review them before that lecture. But anyway, will be around, I think, half of the course, that lecture about the physics. So you have a lot of time. But again, I want to remind you that this is a multidisciplinary course. It requires you a lot of effort from you. This one I know. In my part, I try to simplify this course as much as I can, but on the same times, I want to give you as much as information as I can about everything that you should know. I know that the previous professor, which is also my supervisor, like a little more, I think, let's call it Norwegian style, which is give you a brief introduction about the things, and then you have to go on your own through all the topics in detail. I'm okay with that, but I think the class is mainly I want to give you as much as information as you can, because if you come, I think you should have as much as information and maybe spend less time maybe home. So I should give you all the information you need in class. So this is my at least way to think. Then again, I'm not I don't have anything against other way to teach, but this is at least the way that I used to do.
Yeah.
And
Could you
yes, please.
write, like for example, before we actually get to the physical part of it, could you actually write like what we should actually look at and like send a message on
Definitely.
Canvas or something? Yeah.
I can already, as you know, in Canvas, it is already available all the slide I used last year in the Forelesening Notater 2019, and you can look into that if you want. Also to have a look about maybe for your curiosity, which are indeed this kind of concepts. But again, I will also highlight before that class what are maybe the concept that you have to go through.
Okay.
Yeah.
Thank you.
Pardon me.
Yeah, sorry.
Sorry. May I leave, Luca, because I have another session at
No problem, no problem.
12:15.
Feel free to leave. See you
Yeah,
next time.
thank you. Yeah, see you next time. Thank you. Thank you.
Short question, Luca. Do you have time to consider if we will do any labs physically or?
Yeah, regarding that, I went to the lab after our class last time, and I've looked about the placement of the tables. I definitely have a solution for that, but I have to review it a little, maybe just today, and then I will maybe write in Canvas today or maybe in the weekend how it will be.
Yeah.
My idea is that to minimize the contact with all of you, and in order to reduce the risk of any contact between all of you, there will be lab, and you will have I already saw which seat or which chair you should use. There is more than 2-3 meters between each other with this kind of placement I have thought. But there will be also one member per group at a time. So there will be maybe 2 sessions. In one session, there will be one member of the group. In the other session, there will be the other member of the group. This because talking with Jorgen and how's he called?
And Geir.
Geir, yeah,
Yeah.
Geir.
Yeah.
They were saying that also between same member of the group, there should be a certain distance.
Yeah.
So for this reason, I think that maybe it's better to split the group also, but this defy a little the purpose of the group in some way. I can understand, but this is my proposal. If you have any other better idea, very welcome.
Yeah, as long as we can have labs, that's the important one, because this would be really difficult if we can't have the labs. But I'm positive to all solutions.
I think the labs is a very important part. So I'm trying to do a lot of things as much as I can to make you do that. If someone of you has particular concern, please send me a private email, and I can then arrange a particular time if someone of you has some particular situation or whatever. I can take it into account, so don't be shy, and I will try to do as my best as I can. But I have to know it, because otherwise then you will be kind of have the same arrangement as the other students.
Thank you.
Yeah, so any